Hello students, in today's class we'll be looking for few points, okay? So these points are basically under the topic of points to ponder. What does the topic itself mean is that these are the points which we have seen in our chapter and we have accepted it without any question. Now it's time for us to question it and understand the basics behind it. Like there are these statements which are bit of controversial. See, the first statement, current is a scalar. Although we represent current with an arrow, currents do not obey the law of vector addition. That's the current is a scalar also follows from its definition. The current I through an area of cross section is given by the scalar product of two vectors. See, we know the vectors give us two products. One is dot product, dot, okay. This dot product is scalar product. Another name for the dot product is scalar product. Similarly, another thing which we will see in the vectors is a cross product. This cross product is also known as vector product, and this cross product is used mostly when the product gives us vector. But see over here, I we are getting is a scalar. We have seen I in our text as written in bold letters or a letter with an arrow. Okay. Now the question arises, why isn't current if not a vector quantity? Why it is a scalar quantity? Here, if we see this particular cross section, there are the movement of electron in this direction as well as in this direction. It will be very much clear when we will be reading about semiconductors and diodes. There is a motion of electrons in both the direction. The minority will flow in opposite and majority will flow in the same direction. So when the more number of electrons are going from this point to this point, then the overall net movement of current will be seen in only one direction. And in this, there is a coverage of a distance. And we can reverse the direction of current also by applying a reverse voltage. So it is a scalar quantity where we are multiplying the this one, our J, that is current density, with our displacement. Okay, J is current density, which is also a vector quantity, current density, and then del S is a displacement. Again, it's a vector quantity, displacement. Now, moving to the next statement. Refer to the VI curve of resistors and diode as drawn. The resistor obeys Ohm's law while the diode does not. The assertion that V equals to IR is a statement of Ohm's law is not true. This equation defines resistance and it may be applied to all conducting devices whether they obey Ohm's law or not. The Ohm's law asserts that the plot of I versus V is linear and R is independent of V. I'll explain it. Kindly pay a little attention. This is one of the important statement. When we are going with Ohm's law, under Ohm's law, we read one equation, that is voltage is equals to the product of current and the resistor in the circuit. This Ohm's law is not valid for diodes. But this equation is valid for diodes. Equation valid for diodes. So, from this statement, it is said that Ohm's law is valid only for the conducting devices. Conducting devices. But this equation V equals to IR is valid for all the electrical circuits, whether the electrical circuit follows Ohm's law or it do not follow. Now, similarly, there is another equation which is also a bit of controversial, that is electric field equals to resistivity into current density. E equals to rho into J. Okay, leads to another statement of Ohm's law, that is a conducting material obeys Ohm's law when the resistivity of material does not depend upon the magnitude and direction of applied current. There are the two concepts in this statement. Okay, in this statement which I am marking in this particular statement are do not depend upon the voltage applied. Do not depend upon applied voltage. Okay. Similarly, the electric field applied to a electrical circuit will not affect the resistivity of the wires, resistor or any other electrical equipment in the circuit. Rho independent of electric field applied. So this basically states that the resistance of a device or its resistivity are self-oriented or are proportional constants, or basically are constant which depends upon the material but do not depend upon the magnitude of other electrical things, such as like other electrical factors, we will say, like applied electric field, applied voltage, current passing through it. All these things do not change the resistivity or resistance of an electrical equipment. Okay, hope these 2 points are very much clear. These points are exam specific as well as are entrance exam specific, because these are the things where we will see the tricks. So whenever a trick comes, question is generated from there. Okay, so kindly pay a little more attention here. Now our point number 3, homogeneous conductors like silver or semiconductors like pure germanium or germanium containing impurities obey Ohm's law. So these are the conductors which are having very low, like very high resistance. Silver, you have seen silver being a noble metal. Okay. Similarly, we have these semiconductors like germanium or any other semiconductor which is containing the germanium impurity. Okay, these semiconductors and conductors follow Ohm's law, but there is a condition, and this condition is that up to some certain range of electric field values, if these electric fields are strong, are more than these certain values, then not only these conductors or semiconductors, but all the conductors and all the electrical equipments which follow Ohm's law will deviate from the Ohm's law, show departure from the Ohm's law. Point number 4. Motion of conduction electrons in electric field. Like we are having these electrons, many electrons. When we provide electric field to them, they tend to move, align themselves first in one direction, and then they tend to move. But there is the two contribution, how these electrons are moving. Okay, so motion of conduction electrons in the electric field E is the sum of, first is motion due to random collision, and second is due to the applied electric field. Random collision is that this is one electron, this is another, and similarly there are n number of electrons in a given volume V. So these electrons, when moving in the straight direction or straight path, they tend to meet another electron and will collide with each other, and then they will change the direction from here to here. So this is a zigzag motion which is due to the random motion. So this random motion also creates current. Okay, this random motion also makes current, and if something is producing current, we can say that this is a conducting body. And another thing is that is due to the electric field. Now once we have applied electric field, these electrons will tend to show more motion, and hence there will be flow of the charges which will lead to the current, flow of charges or electrons which will lead to the current. The motion due to random collision averages to 0 and does not contribute to the drift velocity. This is drift velocity. Okay. So contribution is not exactly null. Not exactly null, but some contribution is always there. Okay. This is something written in the book we have to follow, but in practical, if we see this summed up random collision current is not zero. You can see this example, like if you have plugged in your mobile phone and then suddenly you are removing your mobile phone from the charge, and after some time there is no current in your home, electricity is cut short now, and we are not aware, we put our phone on the charge. We will see that for some second, like 1 second or 2 second, our mobile phone will show charging. Okay, so that is the accumulation of the current in that electrical motion or in that electrical tube, and some amount is contributed by the random, but the random motion do not produce current which can show us any sort of significance. Okay, thus is only due to applied electric field on the electron. Now point number 5. The relation J equals to rho V should be applied to each type of charge carrier separately. In conducting wire, the total current and charge density arises from both positive and negative charges. If we are having 2 or 3 charge carriers, 2 or 3 charge carriers, the formula J equals to rho E, rho V should be applied separately to each. Why so? Because in a conducting wire, the conduction is due to both positive and negative charges. Okay. So current density equals to resistivity in the positive plus voltage of positive plus resistivity in negative into the voltage of negative, where resistivity can be simply added up. Now in a neutral wire carrying electric current. So this is a neutral wire. This neutral wire is carrying some current. So in this case there is no positive end and no negative end. So overall there is no rho plus and rho minus. This will give us overall a rho, because our rho plus is equals to negative of rho minus. Okay, so this is rho. Now V plus is approximately 0, which gives us rho equals to 0, and J equals to rho minus into V. Thus relation J equals to rho V does not apply to total current charge density. Okay, if someone is saying that J total equals to J1 plus J2, then no, it is not true. We have to find separately J1 and separately J2, okay, and then go for the summation. Now the sixth point, Kirchhoff's function rule is based on conservation of charges, and the outgoing current add up and are equal to incoming current at junction. Bending or reorienting of wire does not change the validity of Kirchhoff's junction rule. So there is a junctions rule in the Kirchhoff junction rule. In this rule we have read about the incoming current on a junction. Incoming current in a junction equals to outgoing current from the junction. Outgoing current from junction. Okay, so if I make a junction like this, and these are the current coming inside and these are going outside, then I'll name it as I1, I2, I3, I4, I5, I6 and I7. So here we will see that I1 plus I2 plus I3 minus I4 minus I5 minus I6 minus I7 will give us 0, which will give us that I1 plus I2 plus I3 equals to I4 plus I5 plus I6 plus I7. Okay, so this is our junction rule. At this particular junction the current is 0. Now in case I have bent this wire I7 as this, I7 is bent like this, or I have bent our I1 like this. So these kind of structural complexities will not change this rule, won't change Kirchhoff's junction rule. Okay, so this is the our last point in this chapter to understand. Here the chapter is finished, and in this chapter we have covered about current, electricity, then various factors which are related to current like current density, drift velocity, and then we have covered Ohm's law. In contrast with the Ohm's law, we covered resistors. Then we drawn the graphs of V versus I. Then we have understood the properties of conduction in metals or the conducting material. We tried to learn the combination of resistors. Next to it, we moved on to little advancement in the electricity, where we read about the cell, EMF, internal resistor, internal resistance. After reading these very basic terms which gives rise to the building, these are like the building blocks, we built up to the principles like Kirchhoff's rule, where we read the two rules. One was junction rule, as we have seen, and another was loop rule. From this Kirchhoff's rule, there was the birth of principles. These principles are, birth of applications. And these applications are Wheatstone bridge, and potentiometer, and so on. So these are the topics which are covered in the chapter number 3. This chapter number 3 is easiest chapter as well as is of primary importance in various competitive examination. It has simple numerical based on Kirchhoff's rule and simple numerical based on the combination of resistors. Hope you enjoyed reading this chapter with me. Stay tuned for the upcoming chapters and lectures where we'll be learning physics in more creative and understanding way. So have a good day. Bye bye.